This is a hardened induction question. And it says, show that the sum from r equals 1 up to n of x to the r minus 1 equals this product here, or this quotient really, by mathematical induction. So it's the same process, but a good idea in these questions, firstly, is to write out what we've got. So you know the sum, okay, means a series. So if we start with r equals 1, and if I sub in r equals 1 here, I get x to the 1 minus 1, which is 0. So I get x to the 0 plus, and then if I sub in 2, I get x to the 1 plus, if I sub in 3, I get x squared, etc. So that's going up. The last term is n, so it's going to be n minus 1. And I want to show that that sum equals 1 minus x to the n on 1 minus x. So we start as normal. Step 1 is proving true for the smallest n, or r in this case. So prove true for n equals 1. So the general term is this one here. So we sub that in and let n equal 1. So if x to the r minus 1, if r is 1, that's x to the 0, which equals 1. That's the left-hand side. And the right-hand side is 1 minus x to the n and 1 minus x. And we want this equal to 1 also. So it's 1 minus x to the 1 on 1 minus x, which is in fact equal to 1. Therefore the left-hand side equals the right-hand side. Therefore proven true for n equals 1. So step 2 is our assumption, which we use in step 3, and that is not prove, assume true for n equals k. So wherever we see an n, we write a k, otherwise we leave it. So what our assumption is from r equals 1 up to k now, of x to the r minus 1, the sum of that equals 1 minus x to the k on 1 minus x. So that's going to be our assumption into part 3. That's in k. Might make that a nicer k. Right, and step 3 is then, this is what we want to prove. We need to prove it's true for n equals k plus 1. So what we want to show is that the sum from r equals 1 to k plus 1 now is x r minus 1, 1 minus x to k plus 1 over 1 minus x. Remembering, whenever you've got an indice where there's a plus or a minus, you can split them up. Okay, so what we need to do in this one is, we've got the assumption here, and up to n equals k, we've assumed that it equals this, so we can sub in for this. So let's write this one out longhand and then make the substitution. So let's go. So I've got x to the 0, the left-hand side, is x to the 0 plus x to the 1 plus x to the 2 plus, now if I sub in k, so if I'm looking at this one here, if I sub in k, I'll get x to the k minus 1. And we know, if I put that in brackets, that's all of that. It's all of those terms added up. We know I can replace it with that. Plus, so I've subbed in k, but now I need to sub in k plus 1. So the only remaining term is x to the k plus 1 minus 1, which is just x to the k. Okay, and we need to show all of that equals this left-hand side here. So in brackets here, I know that equals that. That's our assumption. So I'm going to replace that 1 minus x to the k over 1 minus x plus, and that is x to the k. So this is what the left-hand side looks like. Now I've got to make it equal to that right-hand side. So how about we take a common denominator, and the first fraction is 1 minus x to the k plus, and then I've got x to the k into 1 minus x. And if I simplify this, now x to the k times x to the 1. Well, that's got an indice of 1, so if I multiply two things that have the same index, if I multiply two things that have the same base, I add the indices. Okay, and that's all over 1 minus x. So minus x to the k plus x to the k, they cancel. So what I have is 1 minus x to the k plus 1 all over 1 minus x, which was equal to the right-hand side, if you look back. So therefore it's proven true for n equals k plus 1. Therefore statement is true as proven by mathematical induction.